anatomists and physiologists. This video is part 4 of our cardio series. This video is all about the mechanical events and the cardiac cycle. So let's jump into it. So when we talk about the cardiac cycle, this is a new word, so I'm highlighting it. The cardiac cycle is just one heartbeat. It's all of the mechanical events that happen in one single heartbeat. And so there's some new words, and I'm going to highlight them in pink just because pink sounds fun to me today. So there's some new words. One of the words is systole. Systole is one of those new words. It's spelled like systole, but you say it systole, and that is synonymous with contraction. So atrial systole means atrial contraction. Similarly, diastole is relaxation. So that's when we come back to kind of that starting position, relaxation of that muscle. And something to remember always is that whenever there's a pressure differential across a valve, that's when the valves open as long as the valve allows, okay? So valves open when pressure increases as long as the valve allows. And what I mean by that is if we're going from atria to ventricles, the valve absolutely will allow blood flow that way. But if the ventricles have more pressure than the atria, we can't have blood flow back into the atria because the valve doesn't allow for that. You see what I mean? We'll get there. Okay, so the cardiac cycle has 4 steps. So 4 steps of cardiac cycle. And so I've drawn the cardiac cycle kind of in this list that goes down, but it is a cycle. So your heart will beat and then it'll beat again. And so it's this very cyclical thing. So almost a better way to draw it is like step 1, step 2, step 3, and then step 3, and then step 4. And then comes back to 1 again. So you have to think about all of the next slides kind of going in this cycle. It's always going to come back to 1. Okay, so now that we've established what the cardiac cycle is, mechanical stuff happening in one single heartbeat. So there's 4 steps. The first step we're going to talk about together is the first step, which is called ventricular filling. Filling of the ventricles. And to kind of set the stage, I guess, for what we're about to talk about, I want to have a really simplified drawing so that everything is kind of easier to talk about. So where I'm actually going to start is just a box. So I'm going to start with just a box, and that box is going to represent our heart. And in our heart, we have 4 chambers. So I'm going to divide that box into 4 chambers. We have the top chambers and the bottom chamber. So we have the right atrium, the left atrium, the right ventricle, and then the left ventricle. That's the bottom chambers, the ventricles. And then we have to remember that stuff enters and leaves all of these chambers. So I'm going to use my little eraser. So using my eraser, we have stuff coming into the atria, we have some valves, and then we have some vessels that are leaving the ventricles. Okay, so now that we've kind of established that, so we have some vessels entering the atria, we have some valves, which I'll just leave blank at this moment because the valves are going to be the things that change, and then we have some vessels leaving the heart. And we'll label those. So those vessels entering and leaving the heart all have different names. So we have our vena cavas, IVC and SVC. So I'll just do vena cavas for all of the ones. That brings blood in. In the left atrium, those vessels would be the pulmonary veins. We're only going to label this once because then we'll just kind of know what everything is. Leaving the left ventricle is the aorta, and leaving the right ventricle is the pulmonary trunk. So now that we've kind of established that, we know that there's valves here. We have valves, the AV valves, and we have the semilunar valves. And we'll talk about what's going on in each of that. That's the thing that's going to change, okay? I should draw Blood goes here, and then blood will eventually leave. Okay, that's like kind of our direction of blood. So ventricular filling, we have to think about. Ventricular filling means filling of the ventricles. A lot of times in anatomy and physiology, these words sound so confusing, but when we break them down, this step is literally filling of the ventricles. Ventricles fill with blood. Ventricles fill with blood. And so what happens here is that we have to think about what's going on in our valves. In our valves, and I'll draw the valves in blue, what happens in ventricular filling, in order for the ventricles to fill, blood has to go from the atria to the ventricle. So those valves have to be open. They have to be. So the valves are open. So I'll draw like my valve, my AV valves open. So AV valves open. AV valves are open, which means that blood can flow freely from the atria to the ventricles. And this happens because the pressure difference, remember pressure opens valves as long as the valve allows, okay? So because the pressure in the atrium is bigger than the pressure in the ventricles, that allows the blood to flow through. So let me draw that or write that down for you. And that's because the pressure, big P, in the atria is bigger than or greater than the pressure in the ventricles. The pressure in the atria is bigger than the pressure in the ventricles. That's why the valves are open. So the atria are so full of blood that blood has to flow and open those valves, okay? The other thing that's happening here is that our semilunar valves are closed. Semilunar valves are closed. So AV valves open and the semilunar valves are closed. And the reason for this is because the pressure in the ventricles is smaller than the pressure in the aorta or the pulmonary trunk. So because the pressure is bigger here and here, the ventricles can't force blood through that valve because the pressure is just too high on the other side of it. So pressure opens valves as long as the valves allow. Okay. But that's really important that those semilunar valves are closed because that allows the ventricles to fully fill with blood. That's important. Okay, so the maximum amount of blood that the ventricles can hold, like the maximum fullness that they can possibly be, actually has a special name. So maximum volume of ventricles, that's called end diastolic volume, or EDV, end diastolic volume. And that's something that's a new word, and we're going to keep talking about that because the ventricles are filling with blood. So what happens here now, so we have blood flowing from the atria to the ventricles. And this happens because atrial systole is happening. So the atria, let's see, I need a new color, don't I? Atria are in systole. They're contracting. And remember that this is kind of like, we say it's step 1, step 2, step 3, step 4 in this cycle, but it's kind of like, it's not that black and white because stuff changes from the start of step 1 to the end of step 1, okay? So systole starts at the start of step 1 and kind of is maximal atrial systole at the end of step 1. Does that make sense? We'll keep talking about it. And this happens, this spread of systole happens, or this increase of systole over time happens because we have the SA node way up here. And that SA node will spread that signal of depolarization because all those cells are connected. So SA node will spread to AV node, and then that'll cause all of the atria to be in systole, and that's what helps further push that blood into the ventricles. But after that systole, that wave of depolarization passes, then we kind of start to diastole, to relax at the end of it. So remember that this is kind of like a wave. It doesn't just turn off and on all the time. Okay, so that is step one. This was probably the longest slide we're gonna spend on, because now that we've done this once, then we can just keep going. Okay. So that was step one, ventricular filling, ventricles fill with blood, atria, systole, okay? And now our next step is called isovolumetric contraction. Iso, that word part iso means same, volumetric means volume, so same volume contraction of the ventricle. And most of this is with respect to the ventricles, because the ventricles are what send blood to the rest of the body. Okay, so back to my box here, which represents my heart. I have all of my chambers. I have my aorta and my pulmonary trunk. I have the vena cavas, and I have all of the pulmonary vessels or veins coming in. So I have a little erase there. Boop, and a boop. Oh, and another boop. Okay, and then let's label real quick. Actually, you know what? I'm going to copy this so we don't have to keep drawing it. Copy. Okay. So like I said, I'm not going to go back and label everything because we've done it once. So in isovolumetric contraction, what happens is our AV valves are closed. In isovolumetric contraction, our AV valves are closed because we're at the same volume. AV valves are closed, AV valves are closed. I'll actually use a thicker marker here. AV valves, and our semilunar valves are also closed. So why this stage is called isovolumetric is because the ventricles stay at the same volume because the valves are closed. Everything is stuck in there. All the blood is stuck in there. So the AV valves are closed. Those are closed. And that's because pressure. The pressure in the atria is less than the pressure in the ventricles. The semilunar valves are closed for a very similar reason. They're still closed from the last step too. So the pressure in the ventricles is less than the pressure in the aorta and the pulmonary trunk. So because the pressure is less now in the atria, because they're in diastole now, but now the semilunar valves, they're still closed because the pressure is still higher in those great vessels leaving the heart. It's isovolumetric. The ventricles stay at the same volume, but this is like such a tiny amount of time. This is a very, very short step. Like the ventricles, they're just about to contract. They're about to contract. Okay, so that is step 2, isovolumetric contraction. And remember, that's a very small amount of time that occurs for. Alrighty, so now we want to, oops, paste. There we go. Okay. So we have our same situation, our vessels coming and leaving the heart, our valves, all the things. This stage is called ventricular ejection. To eject something means blood is leaving. So blood leaves ventricles. Notice that I'm kind of putting this name of the cycle in my own words. I think you should do that too because it helps us understand. When we understand, then it's a lot easier to like keep it in our brain. Okay, so ventricular ejection, what's happening here is that blood leaves the ventricles. Our AV valves are still closed. Our AV valves are still closed. Our semilunar valves, though, are open, which makes sense if we're having blood leave the ventricles. So AV valves, those are closed for the same reason as last. Pressure in the atria is less than pressure in the ventricles. Semilunar valves, though, are now open. Those are open because the pressure in the ventricles is now more than the pressure in the aorta and the pulmonary trunk. Why does the ventricular pressure rise? It's because the ventricles are contracting. The ventricles, I need a new color, are in systole. They're contracting. The ventricles are in systole, they're contracting. When the muscle contracts, that makes more pressure in that chamber. When the pressure rises, because we're shrinking that chamber by contracting it, that forces these valves open. The pressure in the ventricles then surpasses the pressure of that great vessel leaving the ventricle. So pressure opens valves as long as the valve allows. And in this case, the semilunar valves, they're allowed to open. The last stage of the cardiac cycle is isovolumetric relaxation. Remember, another word for relaxation is diastole. It's still isovolumetric, meaning same volume. Relaxation of ventricles. That means that the ventricles, they're just still not, the ventricles are still not allowing blood in or out. Okay, so let's look at what's happening with the valves. No blood is entering, no blood is entering or leaving, so that means that all of the valves are closed. AV valves, semilunar valves, all closed. That's kind of the nice thing about the isovolumetric part. You're like, oh, all valves are closed. So the AV valves are closed. That's because the pressure in the atria is less than the pressure in the ventricles. The semilunar valves are closed, and that's because the pressure in the ventricles is less than the pressure in the aorta and the pulmonary trunk. So pressure opens valves as long as the valves allow, and in this case, the valves don't allow it, so everything's closed. This is the beginning, and remember, this is like a spectrum in isovolumetric contraction. The ventricles, they start really early, the stage in diastole. And then they finish, very much so, in diastole. So I'm going to circle back one slide, don't get dizzy. When we're in ventricular systole, we push blood out. It's nearly impossible to push every single last bit of blood out of that ventricle. As that ventricle is in diastole, there's a little bit of blood that remains in there. That blood that remains there has a special name. That's end systolic volume, or ESV. End systolic volume. That's the blood that remains in the ventricles. We're going to come back to that too. So our ventricles are relaxing, and remember, this happens over the course of the stage. As our ventricles are in diastole, at some point, the atria are going to fill enough with blood and create enough pressure, start to systole, enough to fill then that ventricle, because that valve will open, and that will put us back at step one, okay? So eventually, at the same time that the ventricles are in diastole, the atria are still filling with blood. As the atria fill enough with blood, start to systole, because the SA node lives right there. As those atria start to systole and fill enough with blood, create enough pressure, that will open the AV valves and start the whole thing all over. So go back a handful of slides to step one. Okay, so that's the cardiac cycle. That is the cardiac cycle. Okay, so now that we've gone through those steps, and remember, it's a cycle, so it keeps going. The cardiac cycle is the cycle of one heartbeat, all the activities that happen in the heart. And when you think about what's a heartbeat, if somebody would be like, what's a heart sound like? You'd be like, lub-dub, right? Ba-boom, something like that. Those sounds that you make are sounds that the heart actually makes, that lub-dub sound. It's because it's valves closing. That's kind of what that sound is. And so your textbook talks about two major heart sounds. So we have the first heart sound, the lub part in lub-dub. Oops. Lub. So that's the lub part. That's the first heart sound. That happens because, and that one's usually a little bit louder, right? If you were to do a heart sound, you'd be like lub-dub. That happens because it's the AV valves closing. AV valves closing. AV valves closing. And then the second sound, it's usually a little bit quieter, and that's when the second heart sound, that's when the semilunar valves close. That's the dub part. That's the semilunar valves. But of course, there's two AV valves and two semilunar valves. So if we were to really, really break it apart, we could hear four heart sounds distinctly. And what this picture is showing you is if you use a stethoscope, you know, like the ear thing with the little bulb on the end, you could listen to the heart in these four regions and listen to each valve. So at the doctor's office, this is one of those things that they'll do on your chest to make sure that they can hear all those valves. And that word for listening to the heart has a special name. So it's called, I have my spelling list here. Okay. That word is called auscultating, or listening to the heart. So we can listen to those different regions of the heart to hear what's going on inside that valve. If our valves aren't working properly, then our heart sounds won't sound like lub-dub. They'll sound a little bit different. So for example, like a heart murmur is one of those abnormal heart sounds, and murmur is like, it's like mumbling. That's what the word murmur means, like in English. So a heart murmur is when your heart sounds kind of sound like mumbling, and that usually happens because of valve sounds. So if blood is running into obstructions, but heart murmurs are also really common in the elderly, also really common in kids, even when they're healthy, just because the heart is growing in children or the heart is gradually weakening in the elderly. But sometimes when we hear it in adults, that can be some indication of a valve problem, like it's not closing properly. We would call that incompetent valves. If it's not closing properly, incompetent valves. Or the valve can't open all that well. It gets a little too hard. We call that a stenotic valve, a hard valve. So that just doesn't sound like a normal lub-dub sound. It sounds a little bit different. And if you were in that field, you would have a really trained ear to hear for those types of things. Okay, so that is heart sounds. And we'll be able to talk about this a little bit more when we get into the lab as well. Okay. So the last part of this lecture is the cardiac cycle. The cardiac cycle consists of one major graph, but there's some other bits I want to show you. So this is from a focus figure 8.2 in your text, so I think you should go look at it. I'm going to zoom in on all these things, but I want to show you that there's one part and then there's another part, but it's kind of the same graph. Notice this graph is the same as what is on the first graph. Okay, we're going to break all this down. All right, so what we're looking at here is each of the 4 steps in the cardiac cycle. So each of the 4 steps in the cardiac cycle are depicted in this graph. Each of those 4 steps. instead of drawing like our simplified heart model and all the things. When we talk about the cardiac cycle, the biggest thing to know and remember is that I'm going to write this down, that's so important. Electrical activity like repolarization, depolarization, yada, 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 all that stuff. Electrical activity leads to mechanical activity. What I mean by this is that the electrical stuff, the depolarization, the repolarization, leads to the contraction or the relaxation, the systole or the diastole. And that's what propels blood through the heart. That's the important thing. And this happens, yes, because of electrical activity, but that mechanical activity, the pressure differences, that's what pushes blood throughout the body. And opening and closing valves, as long as the valve allows, okay? So we have some different stuff going on here. What's going on here is, first, whenever we look at a graph, we don't just panic. We always try to figure out, what am I supposed to understand from this graph? The first thing is that the y-axis is pressure. So anything that goes up or down is a pressure difference. So pressure going up, pressure going down, okay? And this millimeters of mercury is a really common pressure unit used especially in the cardio unit, okay? So the purple line here that kind of stays pretty near the bottom, that's the atria, the pressure of the atria. The ventricular pressure is depicted in this blue line. And then the pressure of our great vessels, our aorta, our pulmonary trunk, that's in green. And notice that stays pretty high. That stays pretty high. So the ventricles, they need to obtain a ton of different pressures for those valves to even open. What I want you to notice about this graph before we dive into it is that each time a valve opens, which is noted here, right? Each time a valve opens, we get a big change in pressure. So valve opens, look at the ventricles, big change in pressure. A valve opens, look at all of that, big change in pressure. A valve opens, big change in pressure for the ventricles, a little change in pressure for those great vessels. That's a big thing, okay? When the valves are closed, that's our isovolumetric phases. Isovolumetric. So nothing is entering or leaving the ventricles. All right. Okay, so let's jump into a little bit more of a detailed version of this graph, okay? Oh, and something else I want you to take a peek at is at each stage, which we'll talk about, you can see the different heart sounds. So we'll come back to it. Alrighty. So what we're looking at here, I'm going to zoom out just so we can see all the things. What we're looking at here is at the top, we have an ECG. We have our P wave, our QRS complex, and then we have our T wave. And remember that electrical activity leads to mechanical events. So we'd expect that a little bit after the P wave, we'd expect for the atria to start to contract. And look, atrial contraction. That's exciting. Atrial systole, that rise in pressure, okay? So anytime we see electrical activity on our ECG, we'd expect a little bit of a delay, milliseconds, that's how long it is. And then we would expect that mechanical activity to happen, okay? So then here's the exact same graph we looked at on the previous slide. And then the last part here, which I won't talk about as much, is the volume of the ventricles. So the ventricles will increase and then they'll lose their stuff and then they'll increase enough, or again. Okay, so the last part of this page at the very, very bottom is the thing I really care that you think about, okay, is all of the stages of the cardiac cycle, 1, 2, 3, and 4. And notice that they're all corresponded to colors on this graph. So we have light blue, this kind of like dark tan is step 2, the like yellowy, orangey color there in the middle, the lighter one, and then we finish with that dark tan again, okay? So those are our 4 steps of cardiac cycle. That's what's happening. Okay. So let's overlap all of the things that we know about the cardiac cycle, about ECG, and now about pressure differences opening valves. We're going to be here for a minute, so just prepare. So in the cardiac cycle, step 1 is ventricular filling. So step 1 of the cardiac cycle, I'm going to zoom in a little bit here, is ventricular filling. So that's this whole stage. Ventricles fill, and I'm writing it in this blue section because my key just told me that ventricular filling is all of the blue stuff. And if you go back in your notes, what happens in the ventricular filling stage is that we have our valve that opens because our AV valves open because we have a rise in pressure in the atria because atrial systole happens. And then all of that blood flows into the ventricles. So now we can take a peek at why this happens. The atria undergo systole because the P wave was like a minute ago. Not really a minute, like a hot second ago. So the P wave, if we were to draw it, pretend that's a straight line. Okay, the atria depolarize. Depolarization precedes atrial contraction, which means that depolarization comes right before or leads to atrial contraction. And remember that the blue line is atrial pressure, so atrial pressure rises. This is when our valve opens. That's when the AV valves open. So the AV valves open, and then the ventricles fill with blood. So that's exactly what happens, ventricular filling. Okay, so then step 2 of our cardiac cycle is the isovolumetric contraction, meaning that the ventricular pressure is going to rise. Ventricular pressure is going to rise. Why does it rise? Because the QRS complex was a hot second ago. The QRS complex is ventricular depolarization on our ECG. Ventricular depolarization comes right before, actually causes ventricular contraction. That causes the contraction of the ventricles. So when the ventricles are in that, and remember I told you this, that step of isovolumetric contraction is very, very brief. And look at it, it's very, very brief on our graph. It's not that much time. But the ventricles rise in pressure very rapidly. That pressure then will start to open the semilunar valves, which is the next step, ventricular ejection. That's everything that's in like that orange, lighter brown color in the middle. When we have the next step, that ventricular ejection step, we have the semilunar valves open, everything leaves the ventricles except for like the last little bit of blood. And so we'd expect to see lots of ventricular systole because we just had ventricular depolarization. And yes, systole is what happens. We contract. So this pressure increases, increases, increases even more. And it starts to decrease by the end of that stage. Remember that each stage is a spectrum. So stuff changes from the start to the end of it. The last bit of the cardiac cycle, this last brown bit here, is ventricular, is isovolumetric relaxation. Iso meaning same volume, relaxation meaning relaxing, okay? We would expect on our ECG that right before relaxation, right before we relax, we would repolarize, and that's exactly what happens. The T wave is when the ventricles, those cells of the myocardium in the ventricles repolarize. Electrical events lead to mechanical events, and that's what happens. A very, very brief delay, and then we get that relaxation step of the ventricles. So the ventricles go, ah, everything is good in life. We can relax for a hot, hot, hot second. All the valves are closed because we have the semilunar valves closing there. All the valves are closed. That's the isovolumetric part. And the ventricles, they're now back to diastole. They're relaxed. But that means that we start all over. And our ECG starts all over. And our ventricles start to fill again because we're back at ventricular filling. You see what I mean? So the cardiac cycle graph looks scary. But remember that each of these steps, step 1, step 2, step 3, step 4, it's just a graphical depiction. And each time you have one of these guys, 2, 3. That's valves opening and closing, okay? Anytime the blue line is really the line that we care about. Anytime that line changes its pressure, we know that something's happening. Here, we're starting to undergo systole, contracting. We're still undergoing systole during ejection. We start to diastole as we come back down to where we started again. That's the cardiac cycle. And the cardiac cycle happens because of the ECG, because of the electrical events. The electrical events lead to the mechanical events. That's what I want you to know, okay? This leads to relaxation. Lots of folks get scared by this graph, but it's not scary because it's just a graphical depiction of electrical events lead to mechanical events. The ventricles fill and push it out and fill again. That's what happens. I'd love to chat with you more about this if you have any questions, so please don't hesitate to ask.